Okay, so we've been kind of learning bits and pieces of all the little details that go into a polynomial and what the factors look like and all that stuff. Now we're going to get into a little bit more detail. First thing we'll talk about is the remainder theorem. Okay, the remainder theorem is an alternate, not necessarily that you need to do it this way, but it's a different way to find a remainder. Okay. Actually, let's go ahead and just do this first example together. So, you guys remember how to do synthetic, right? How do I set it up if I want to divide this by x minus 1? What do I put in the little box here?
1.
Okay. And then the coefficients are 2, negative 3, and 4. And first thing we do is just bring down this first value. We multiply. We get 2. We add. Negative 1. Multiply again. Negative 1. Add that up. You get 3. So what is the remainder? The remainder is 3. Right. We've already known how to do that, right? We learned synthetic last time. You can do synthetic, and if there's a remainder, there it is. You just write it down. What the remainder theorem is telling us, this little value that we put in this box, if you just substitute it into the polynomial, that is also going to be equal to the remainder. So instead of doing synthetic division, especially those of you that forget zeros as placeholders, right? This might be a better option. Okay, so if you just plug in 1, we get 2 times 1 squared minus 3 times 1 plus 4. And if you simplify, 2 minus 3 plus 4 is equal to 3. So regardless of whether you do synthetic division or if you just plug in the potential root, which is 1, you get the same answer. You guys see how that works? Okay. So you have two options now to find a remainder. Either do synthetic division like we learned last week, or if you want to just plug in 1, plug it in, you get your remainder that way. Okay? This one, the next theorem here, the factor theorem, we've already kind of been dealing with. We just haven't really formalized it. Okay? So if we know, let's just start from the beginning. If I plug in a value c and I get 0, that means there's no remainder, right? And if there's no remainder, that means that c is a root or a 0 of the function. And if it's a 0, does it make sense then that x minus c has to be a factor? There's like 3 little connect the dot steps going on there, but from beginning to end, if you plug in a number and you get 0, that number has to be a root, so x minus c has to be a factor. Okay? We've been dealing with that already. The other way around, this one should make sense. If x minus c is a factor, then obviously if I plug c in, I should get 0. That's the whole point. Okay? Now how can we use this? Let's go to part A. Let's go ahead and find the remainder. You know what? Take 10 seconds, 20 seconds, however you want to do it. Synthetic, or if you want to do the remainder theorem. I'm not going to care whether it's remainder theorem or not. Just find the remainder on your own. What are we getting, you guys? 6? Everybody's getting 6? Okay, so whether you do synthetic or if you just plug in 3, remainder is 6. Everybody getting that? Okay. Now, because the remainder is 6, does x minus 3, does it make sense that it's a factor? Yes or no? what does the remainder have to be? This has to be 0 in order for x minus 3 to be a factor. Since the remainder is 6, now this is what they mean by use the factor theorem. Because the remainder is 6, x minus 3 is not a factor. If we got 0 here, then we would know for sure that x minus 3 is a factor. Okay? Any questions on that? Okay. Let's turn the page. And now let's talk about the maximum possible zeros. Okay? This is actually kind of like the fundamental theorem of algebra. Okay, but basically, and you've probably seen this, and hopefully you've been kind of connecting the dots on your own. The degree of the function tells us potentially how many zeros or roots there are. Okay? For example, a quadratic. You're thinking 4 because quad, right?
It's 2.
Quadratic is degree 2, right? So we're not going to go ahead and do this, but let's just work with me here. If I have x squared minus 4x plus 3, okay? We have a degree of 2, and you've seen that how many solutions would this have? Typically there's 2 answers, right? Not always, but at most, whatever the degree of the polynomial is, at most, that's the number of roots there will be. Does that make sense? So for this one here, we're not asked to find the zeros, but looking at the degree, what's the maximum number of zeros that we would have? That's right. Okay. Does it mean that there's 5? No. We could have maybe 3. We could have 1. Now, I'm going to add this in because it's going to come up later, and we might as well just touch on it now. If you include multiplicity and non-real solutions, it's guaranteed that there's exactly 5. So if you include multiplicity and non-real answers, you know, where we get those i's, if we square root negatives and whatnot, not only is 5 the maximum number, there has to be exactly 5 if you include all that. So what I mean by that is this. Separate example before we get into this P's and Q's business. Let's say I have something like this. Okay? If we're looking at this, and if I just ask you how many real roots there are, here I would get what root, or what 0? 3. What about here? -1. If I set this equal to 0 and tried solving, I wouldn't get any real answers. It would be imaginary answers, right? So this one would only have 2 real answers. Even though, if I look at the degree, this is x squared, x squared. This is a degree of 5. Okay? That's the maximum number of roots. In fact, here there are only 2 real roots. Okay? But now, if we count multiplicity and we count imaginary answers, watch what happens. 3 is a root, right? But what's the multiplicity? So we basically count that twice. That's what that means. Does that make sense? So there's 2 right there. If I take this one, we have a root of 1. So far that's 3 total. Does that make sense? Here, if I go ahead and set it equal to 0, and then square root both sides, I know this is now a review of what we did earlier, but this would be plus or minus I. There are 2 imaginary answers right there. You see what I'm saying? So we got 1, 2, 3, and then 4, 5 because of the multiplicity of 2 there. If you count imaginaries and multiplicity, exactly 5 all the time. Well, depending on the degree. In this case, 5. Just a little bit of painting a picture for later. Right now, very simple. If the degree is 5, you just say at maximum there's 5 zeros. Okay? Can you guys handle that? Okay. Last thing we're going to talk about today is the rational zeros theorem. Okay? So now look, you will be able to use a calculator for these exams that we're going to do. You basically need to know the rational zeros theorem and how it works. But as far as actually finding zeros and whatnot, we're going to approach this with the fact that we have a calculator available, and then you're going to use that to help you demonstrate that you understand how this works. Okay, but for now, here's the rational zeros theorem. I'll summarize it a little bit differently, but essentially, you look at the very last coefficient. That's where we start. Factors of this number are what we call the p's. Okay? The leading coefficient. The factors of the leading coefficient are what we call the q's. What the rational root theorem says is that if there are rational zeros, that they come from a list of potentially several options, and those are going to be all the possibilities of the factors of this last number divided by the factors of this first number. So you'll kind of see how it's split up. You got p's, you got q's, and then your p over q's. This column over here, this is what we mean by all the possible zeros. Possible rational zeros are always p over q's. Okay? And it's not horribly difficult. It's just you have to be very careful and list everything out. Okay, so we'll do one together, and I'll let you guys kind of finish the page on your own here. But here's how we start. The p's come from this 4. Okay? What are all the numbers that go into 4? What are all the factors of 4? 1, 2, and 4, right? Does that make sense? Now we're going to go ahead and say plus or minus 1, plus or minus 2, and plus or minus 4. Because theoretically, you could multiply negatives and positives together, or negatives with negatives together. Does that make sense? So it could be any of those options. Okay? The q values come from the leading coefficient, which is 2. So what are all the possible factors that go into 2? So plus or minus 1 and plus or minus 2. Everybody good so far where we gotten those lists of numbers? Okay. Now, if this has any rational zeros, this polynomial that we had, if we have any rational zeros, it's going to come from this list where we take all our p values and divide them by the q values. And so for me, the easiest, I don't care if you list them like in smallest to highest order. I just care that you have them all written down. And so I always go like this. Take your first p value and divide it by the first q value. What do we get? 1. And now just divide it by the other q value.
2.
Careful. Plus or minus 1 divided by plus or minus 2 is plus or minus 1/2. Do you guys see where we're getting that?
Yeah.
And so now we've done, okay, I've done all my possibilities with p being a 1 value. Does that make sense? And now I just do the same with 2. Plus or minus 2 divided by plus or minus 1 is plus or minus 2. Plus or minus 2 divided by plus or minus 2 is plus or minus 1. And we have that already, so I'm not going to list it again. You guys see that? Okay. Last one. Plus or minus 4 divided by plus or minus 1 is plus or minus 4. Plus or minus 4 divided by plus or minus 2 is plus or minus 2, which I already have. So I'm done. Okay, so the rational roots theorem says that if there are any rational zeros to this polynomial right here, that it's got to be from this list. So potentially, if you plug in 1, you get a 0 remainder. Or maybe if you plug in -1, you get a 0 remainder. Does that make sense? That's where this is headed, you guys. So eventually, we're going to put everything together and say, here's our possibility of zeros that we could have. Let's see which one of those has a 0 remainder. And if we can do that, that'll get us started in figuring out every other 0 there is. Okay? But again, we're splitting this up into several little lessons. Are there any questions on this? Yes?
So then you do this standard way and like plug in 0 for 1 and so.
So that's a great point. David, I would absolutely do that if these were quadratics only. The thing is that these are cubics to the 4th power and to the 5th power, right? So setting them equal to 0, you're right, like it is here. It may help if we know how to factor it, but a lot of times we won't know how to factor these because the degree is so large. Does that make sense? So that's why we talk about this possible list of roots that might work.
So these are just possible.
Right. They may not necessarily work. Exactly.
We don't need to check it.
Right now you don't, no. But tomorrow I think we'll start kind of putting everything together. But again, we have the calculator, so we're going to really kind of cut to the chase and say, you know what, here's my possible list of roots. Let's use the calculator now to see which one of those is a root. Does that make sense? And then we'll go from there. You guys just have to understand, I need to see and we need to see that you understand what this possible rational zeros is. Okay, so not every number here is going to work. Maybe a couple of them will, maybe none of them will, depending on if there's all imaginary answers. Yes?
So going back to the rational zero theorem,
Yeah, yep.
that technically means that there's only three right out of that four, right?
So you're kind of putting yes,
Yeah.
the maximum possible zeros, yes. So this has a maximum of 3 real zeros. If they're rational, meaning like integers or fractions, those 3 are going to come from this list. Now it's possible that maybe there's only 1 real 0 that's a nice number like this. Then what that means is that there's maybe like radicals for the other zeros. Or we have the i's, exactly.
Okay.
Does that make sense? Yeah. That's a good question. Okay, why don't you guys try finishing the page here, and then I'll go over the answers with you in a few minutes.